guys, so we're going to make a quick video on some periodic trends, and I have a blank periodic table. You guys could get a blank periodic table on the module site or just Google blank periodic table. Okay, so I went ahead and I color coordinated these through S, P, D, and F just so we could keep that in our heads and not forget about the different sub-levels that we have. Okay. All right, let's talk about the periodic trends. So just put up here periodic trends. We're going to take notes also slightly as we do this. So a couple of the periodic trends that we have, the first one that we want to talk about is going to be atomic radius. So atomic radius refers to the size of the atom. Okay, it refers to the size of the atom, and it's measured from the nucleus, so basically the center of the atom, to the edge of one of the atoms. You just measure its radius, and you take the radius squared. All right, so how does atomic radius increase, and what causes atomic radius to decrease? Well, first let's just figure out what the trend is. As we go down the periodic table, so as we flow down this way, we add energy levels. So as we go down, we're adding energy levels, okay? And what do you think is going to happen as we add energy levels? Well, your atom is going to get bigger, therefore your atomic radius increases. All right. So atomic radius increases because we're adding more layers, right? So it's like you put on a sweater, then you put on a jacket, and then you realize that you're still cold, so you put on another layer, and next thing you know, you look like a little puffball, right? Because you're full of layers. So atomic radius increases as you go down because we're adding more energy levels, which is the same as our layers. Okay. Now, as we go across the periodic table, some of us would expect the atomic radius to also increase. However, that is not the case. So as we go across the periodic table, the atomic radius actually decreases. So it decreases. So as we go across, atomic radius decreases. So we understand why it increases, right? We're adding more energy levels. So adding more energy levels. But why is it decreasing if we're adding more protons and more electrons and whatnot? Well, that's actually why it's decreasing. So as you go across the periodic table, the effective nuclear charge is actually increasing. And the effective nuclear charge is basically the neutron pulling the proton, pulling the electrons towards it. Okay, so it's your nucleus that's become stronger and stronger because you're adding protons, and the more protons you add, the stronger it becomes. Now it's going to be pulling the electrons towards it. So remember, the proton is much bigger than the electron, right? And this is the same shell. So here we're talking about the same shell, right? So we're adding more protons, and yes, we're adding more electrons, and that only causes, as you add more electrons and more protons, for the center to become more powerful, and thus trying to squeeze those electrons towards it. So the atomic radius decreases because the effective nuclear charge increases. Charge increases. So this is basically causing nucleus to pull electrons closer to it. All right. So hopefully that explains the atomic radius a little bit to us. Okay, now let's talk about ionization energy. All right, so ionization energy, as we go across, ionization energy increases. Energy increases. Okay, and as we go down, ionization energy decreases. So you'll notice that it is the opposite of so I'm just going to put IE for ionization energy decreases. Now you could change the arrows how you see fit. You can make them all increasing, pointing one side, and so you don't have to worry about this whole decrease, increase. I just kind of change things up a bit. All right, so what is ionization energy? It's the amount of energy. Actually, I should write that here. Ionization energy is the amount of energy required to lose or gain an electron. So the amount of energy required to lose or gain an electron. So ionization energy basically increases as you go here. That means it costs more energy. So it costs more energy to ionize, basically. And the reason it's called and it costs more energy is because the effective nuclear charges increase. Because the effective nuclear charge is holding on to those electrons very, very tightly. So it costs more energy to ionize, to gain or lose an electron, right? To ionize due to increase in effective nuclear charge. All right? But why does it decrease going down? Well, the reason it decreases going down is because we have the atom is getting bigger. So those outer electrons, because those are the electrons we're talking about, by the way, the outer electrons are further away from the nucleus, so they're not as strongly held together. The further you go down, the further the electron is from the nucleus. So it decreases because electrons are further from the nucleus. Are further from nucleus, thus don't feel the effective nuclear charge as much. So they're further from the nucleus, and so they're not feeling the effective nuclear charge as much. Let's see if I can zoom in for you. Oh, I can't. All right. So we've now gone through atomic radius, kind of talked about effective nuclear charge. We just finished ionization energy. Let's go into electron affinity. So electron affinity is going to increase as we go this way. So this is going to be electron affinity increases. electron affinity increases. And electron affinity decreases going down. So I'm going to put that on this side. So electron affinity decreases. So that's a little arrow pointing it downwards. Now, electron affinity, let me make sure I get this correct really quick. Okay. Okay, so it's the electron affinity is going to be the amount of energy required to actually release an electron from its gaseous state. And I'm going to just reread that one more time, make sure I get it correct. Yes. Okay. So the amount of energy required to release an electron is the amount of energy required to release an electron from its gaseous state. Okay, so basically that means your element has to be in a gas, and when it's in a gas, then the electrons can move about. So the amount of energy required to ionize it and turn it into an anion. Okay, so you're going to talk about turning it into an anion. All right, and now the reason the electron affinity increases, so the energy required to release that electron increases, it's due to the effective nuclear charge increasing. Okay, so the effective nuclear charge increasing. Now, some of you guys might think electron affinity, and ionization energy are the same. They're a little bit different. Okay, so ionization energy is the amount of energy required to lose or gain an electron, right? Well, electron affinity only talks about losing an electron, okay? About losing an electron. And remember, as we go across the periodic table, the effective nuclear charge increases, okay? I believe effective nuclear charge is like FEFF or something. It's the abbreviation, but since I can't remember, I'm not writing it down. But effective nuclear charge increases, holding on to the electron very tightly. Therefore, electron affinity increases as we go across. Stronger the effective nuclear charge, the more it costs to release an electron. The bigger the atom gets, the less it costs to release an electron. All right, so now that we have that one, let's go ahead and move on to the next one, which is going to be electronegativity. I love that word, electronegativity. Okay, so we're going to go ahead and circle this box right here, and it's going to have an F on it, and that F stands for fluorine, right? Now, there's a reason why I had you guys do that, so let's go ahead and make another arrow, and I'm gonna do this one opposite. So this one's gonna go up like this, and this is electron affinity, electronegativity. Increases. Okay. So as you go up, electronegativity increases. And you're like, well, what's electronegativity? It is the elements or the atom's ability to attract other electrons to it. So atom's ability to attract other electrons to itself. Right? So it's like basically going, hey, I'm more charming, come to me, right? And then so the higher up on the periodic table you are, the more charming you're going to be, and the more willing those electrons are going to want to go with you. Okay, and electronegativity also increases as we go across the periodic table. Okay, So your ability to attract electrons increases. Okay. Now why? Why is it for these two that they increase the way they do? Well, the reason electronegativity increases going across the periodic table, it's because that positivity has also increased. It has more protons. And if you have more protons, you have more of the opposite charge, and therefore the electrons are going to want to go with you. Okay, so the increase in protons, right, which creates an increase in effective nuclear charge, creates an increase in your ability to attract electrons towards you. So we have increase in protons, which then leads to an increase in positive charge, which leads to an increase in the effective nuclear charge, right? Which means you're going to attract more electrons. Thus, you're going to attract more electrons. Okay. And then why does it increase this way? Or I could have said the opposite, that it decreases going down. And it would decrease going down because your atom is getting bigger and thus it's further away from the nucleus. It increases going up, so the higher position right here, right? You have less layers and therefore your nucleus is more readily available to bond. Well, actually your nucleus isn't bonded, but your nucleus is less shielded, right? So it's less shielded, thus it's projecting that positive vibe a little bit more. Now, the reason I had you guys circle fluorine is because fluorine is the most electronegative element. So I'm going to write most electronegative element. And this one is crucial. It stands at a 4.0. Okay, at a 4.0. That's the highest that the electronegativity values can go, is 4.0. All right. The lowest electronegativity value is actually going to be right over here. So we're going to circle that one, and it's Fr, and that one is francium. So it's the lowest electronegativity value, okay, and that's francium. Okay. Let's do some other ones. Okay. Metallic character. Okay, so let's go ahead and make a line first, showing, just color coordinate. Okay, so showing you guys where your metalloids are at. Okay, so if you draw these ones with me, these are going to be your metalloids. Okay, and metalloids are basically atoms that exhibit both metallic and non-metallic characteristics. All right, so it's going to be, I'm just making sure I got them correct. And these two here. All right. All right, these are your metalloids. Okay, metalloids, one more time, exhibit metallic and non-metallic abilities. All right, so our metallic character increases as we go down this way. Metallic character increases. It goes up, right? And your non-metallic character increases. Now, for this one, I realized I said you increase it as you go up. No, you increase metallic character as you go down this way, and you increase non-metallic character as you go up. And that is because, let's see, these atoms here are all non-metals. These are all your non-metals, okay, including hydrogen there. Okay, so those are all non-metals. That means everything else is a metal, including these ones right here. They're just more radioactive and man-made metals, but these are all metals. Okay. That is it for periodic trends. Okay. So hopefully you guys were able to learn a little bit about this. Couple things too that I could mention that will help us out is polarity on the periodic table has to do with electronegativity. So when you have two elements that you can combine together, they're more electronegativity. When you subtract they're more polar ones. The more polar bonds are created when you subtract the electronegativities, and the higher the value you get, the more polar it's going to be. Example, okay, so fluorine and then francium, and let's say francium is a 0.5 value of electronegativity. Well, if we had an example, this polarity, okay, and electronegativity. All right, so if I had francium and fluorine combined together, okay, and I wanted to know the electronegativity value of this bond, well then I would have an absolute value 0.5 minus 4.0, which is going to give me 3.5, which is going to mean that this is ionic. Okay, so it's highly electronegative between themselves. The higher the electronegativity value, the more polar it is. So this is a very polar molecule. It's actually ionic molecule. Ionic means that the electrons are not shared, the electrons are transferred, because ionic molecules transfer electrons and covalent share. So an example of a covalent one would probably be, let's see, let's just make one up here. Bromine and fluorine combined together. Right, so bromine has a polarity of about 2.3 minus this 4.0, or sorry, 3.3. Okay, minus a 4.0, which gives us an electronegativity difference of 0.7. This is not ionic, it is covalent. And the way that they share their electrons, well, is almost equally actually, because it has such a low electronegativity difference in value, right? So these ones are polar, okay? And you know it's polar because this is not a 0. If this was 0, for example, fluorine and fluorine, you're going to have 4.0 minus 4.0, which is going to equal to 0, which is covalent, and it's going to be non-polar. And this is covalent and is polar, right? So there is some attraction, and electrons are not being shared equally between the atoms. All right, you guys, take care. Enjoy.